Now in this video we will have a look at the improper integrals of type 2. Well, remember now for type 1 the key feature of those integrals were it had a infinity notation in one of these lower or upper limits, right? So that was the key feature of type 1 improper integrals. And for type 2 we have finite range for the function. We have finite numbers for upper and lower limit, and the problem is with the function inside. Okay, I will start with an example in here as well, right? So if we consider the integral of 2 to 5 of the function 1 divided by square root of x minus 2, okay, and if we draw the graph of this function it will be something like this. So you can see this function will have a vertical asymptote at 2, and 2 is one of the it's the limit point of this considered range. Okay, what I mean by a limit point in this case is just the one out of lower or upper limit. Okay, so this is the key feature that we have to consider when it comes to improper integrals of type 2. That is, the function will have a vertical asymptote, and when it comes to the area notation, so this integral will represent the area of the function in between 2 and 5, and for 2 you have a vertical asymptote. In other words, we will have an infinite range in this direction. Remember, for type 1 integrals we had a infinite range for the area in horizontal direction, but here we will get an infinite range for the area in the vertical direction due to the vertical asymptote. Okay, right. So how are we going to find the area, or how are we going to evaluate this integral of type 2? It's almost similar to the previous one, but now here instead of an infinite range of the interval we have a vertical asymptote for the function. So what we can do is we can say if we have an instead of this 2 as the lower limit, what if we have a number which is a little bit greater than 2? Let's consider 2.5. Then we can easily compute the area without any trouble, right? Because you don't have any sort of a vertical asymptote problem at 2.5, hence you can just directly calculate the area of this function. Okay, and how about 2.4? It's the same. Right, you can still calculate the area with the knowledge we have. Okay, so now you can see what we have to do is we should reach this integral from the points to the right side of 2. In other words, we will have the upper limit as the same one, and we reach our integral through a limit. Okay, so our limit should be, now if we indicate this as t, then our limit should be t goes to 2 from the right hand side. This superscript plus sign represents the limit approaching from the right hand side. The reason is you have a vertical asymptote and you can have finite values for the points which are to the right of positive 2. So we reach the integral through those points. So in general, if I describe it, if I described what we have discussed so far, it will be, so we can generalize our result in this way. If we have a continuous function, now this continuity is important, on a to b. Now here we have a function which has a value at a, but it does not have a value at b. That's the reason for having a open bracket at b. Okay, see here a has a closed bracket. That means the function is continuous at a also, but not at b. So in other words, we will get something like, we can get something like this, right? So in this case, the integral we should approach from the values to the left of b, and that is represented by this superscript negative sign. In this case, if the function is continuous on open interval a, closed interval b, that means the function is defined at b but not at a. So a will have the vertical asymptote. Here b is defined. Now this is similar to the example that I wrote here. 5 can be considered as b, 2 can be considered as a. So we should approach the integral from the points to the right of a, and that is represented by the superscript plus sign, right? So it's a very intuitive idea. What we have to do is we just have to approach the given integral from finite values, and here it is to the right of a, and here it is to the left of b, and that can easily be obtained, like that can easily be visualized if you draw the correct diagram. Okay, right. And there's one more thing that I should say. Now see, here the continuity of this function is an important factor behind both these statements, and the function had a discontinuous point at the end of this region, like in the left end point or at the right end point. So here the discontinuity is there only at an end point, right? But what if you have a discontinuity in the middle? Say if we have f where it has a discontinuity at c within this interval. So here we start with a and go up to b, but in between you have a discontinuous point. So what should we do in those cases? Now if I draw a diagram that goes with this one, we can indicate this one as a and b, and how about having a vertical asymptote in the middle? So we have this sort of a situation in the given condition. So what would we do if we have this type? Then what we can do is, now before going into this statement, I should mention one more thing. If this value is finite, we call that the integral converges. That's the same thing that we used in the type 1 integrals also. So if this is finite, we call it as a convergent integral, and if it is not finite, we call it as a divergent integral. Okay, no matter whether we reach from the left hand side or the right hand side, if it has a finite value, we call it as a convergent integral, and otherwise we say divergent integral. So for this part C, Now, as we have vertical asymptotes in both left hand side and from the right hand side of C, we can separately compute these two integrals, right? Now if we take this one, our right endpoint, now if we consider A to C, the interval of consideration will be closed interval A, open C, because at C you have a vertical asymptote. So if we have this sort of a situation, we have to use the left endpoint of this critical number, right? So simply what we have to do is we can calculate this integral with the help of limits approaching C from the left hand side, because that's the place where we reach when we start off with A, right? Left hand side, and if we consider this integral, and then for the next part, for this part we can take the same thing, but only difference is that we should approach B from the we should approach C from the right hand side, okay? Because for all the values to the right hand side of C, the integral will be a finite value, okay? So we should approach C from the right hand side in this case. And as I explained earlier, if these are finite, if this limit value is finite, we say that the integral that we started is a convergent integral, or in other words, the integral converges, okay? And if both these integrals converges, then we can write down the integral from A to B as the addition of these two integrals, right? But if one of these two does not converge, we cannot write down this equation, okay? We had a very similar result for type 1 integrals as well, okay? But the only difference is, in these cases you have finite values for upper and lower limits, but we have a asymptote for the function. But in type 1 we did not have any asymptotes for the function, but we had infinities for the upper and lower limits, right? Okay, so in the next couple of videos we will go over some problems related with this type 2 improper integrals.